In this tutorial video, we'll go over the file structure of the cavity case that was run in the previous tutorial. You'll note that this is the position that we reached in the last video, and this is the working directory that we're in at the moment. Now, although all of this operation can be done within Ubuntu via the command line, it is much easier to do it via a graphical interface. And for that reason, I strongly recommend you install Visual Studio Code and its associated WSL extensions. If you don't yet have Visual Studio Code, it's as simple as Googling Visual Studio Code install and downloading it from here. Once you've done that, go to Visual Studio Code, click on the Extensions tab, and type in WSL, short for Windows Subsystem for Linux, and click the Install button that will be here. I've already installed it, so it's not present. Once you have this extension installed, you can go to your Ubuntu terminal, you might have to restart it, and type code, and then a space, and then the file that you want to open in Visual Studio Code. In this case, I'd like to open the entire directory that I'm currently in, so I just type the dot. This will open a Visual Studio Code window showing the contents of the directory you just specified. Let's take a look at the file structure of the cavity tutorial case. There are a number of time directories with numbers as names, which store the solution of the fluid flow at a given point in time, as indicated by the name. There is the constant directory, which stores the properties of the fluid as well as the mesh that the simulation is run on. There is the system directory, which stores all the settings needed to specify how the solver should run. There are also a number of other files we generated as part of the solution process. Note that before the simulation was run, only the 0, constant, and system directories were present. Let's take a closer look at the 0 directory. We see it contains two files, P for the pressure field and U for the velocity field. Let's start with the P file. Note that I'm using the OpenFOAM extension to enable syntactic highlighting for these dictionary files. You can enable this extension by clicking on the Extensions tab, typing in OpenFOAM into the search bar, and installing the first result. You can now select the OpenFOAM setting if it is not yet selected by clicking on the Select Language Mode button in the lower right corner, searching for OpenFOAM, and selecting the first option. In the P file, we see a standard OpenFOAM header, some metadata about the file, the units of the field, the values of the field within the mesh, and the boundary conditions for each face. The dimensions entry specifies the units of the field in order of mass, length, time, temperature, amount, current, and luminous intensity. The corresponding SI units are kilogram, meter, second, Kelvin, mole, amp, and candela. In this case, we see the pressure field has units of meters squared per second squared. Note that these are not the units of pressure which would ordinarily have units kilogram per meter per second squared. But since we are using a solver for an incompressible fluid, namely icoFoam, the pressure is instead specified as kinematic pressure, that is, pressure divided by density. The internal field is specified as uniform 0, which means the pressure is set to 0 everywhere inside the mesh. We see the moving wall and fixed walls have type 0 gradient. This means that there is 0 pressure gradient perpendicular to the walls. Front and back has type empty, meaning the pressure equation is not solved in its direction. Note that all OpenFOAM cases are solved in 3 spatial dimensions, x, y, and z, by default. So to run a 2D case, we must specify the boundary condition on the front and back of the domain to be type empty. If we go back to ParaView, we can view each boundary by selecting the foam.foam file in the pipeline browser, scrolling down to the mesh regions, deselecting the internal mesh, and selecting the boundary we're interested in. Then click Apply. Here is the moving wall boundary, the fixed walls boundary, and the front and back boundary. Note that boundaries are usually called patches in OpenFOAM, so this would be called the front and back patch. Going back to the P file, we can now see why the boundary condition on the front back patch is empty, since the case is 2D. Moving on to the U file, we again see a standard foam header, some metadata about the file, the units of the field, the values of the field within the mesh, and the boundary conditions for each face. The units this time are meter per second, which is what we would expect for velocity. Since velocity is a vector, we must specify each component separated by spaces and surrounded by circle brackets. In this case, the internal field is set to 0 meters per second everywhere. Note that we must specify all 3 components, even if running in a 2D case. The moving wall patch has a fixed value of 1 meter per second in the positive x direction, which agrees with what we saw in ParaView. The fixed walls patch has a type no-slip, which is equivalent to having a fixed value of 0 meters per second. As with the P file, the front and back patch is specified as empty to stop OpenFOAM from solving the velocity equation in that direction. The remaining time directories contain the same files as the 0 directory, as well as some extra files that icoFoam wrote. Looking at the new P file, we see that, instead of a uniform value, the internal field is now specified for each of the 400 cells. The U file has a similar change. The phi file specifies the volumetric flow rate through each face. This is an intermediate field used by icoFoam as part of the solution process. This file was written by icoFoam, but is not required to be present for it to function. There is also a uniform directory, which is not always present in OpenFOAM sims. This contains the time file, which specifies more accurately what the time of the solution is. The cumulative continuity error file shows the amount by which mass conservation is violated, which is quite small. This file is not usually written by other solvers. Finally, the function objects directory contains data relating to any additional functions specified by the user in the control.dict file, which we will go through later. In this case, no additional functions were specified, so the only file here has no data. The remaining time directories are very similar to this one. Let's look at the constant directory. It contains a file called transport properties, which specifies what the kinematic viscosity of the fluid is, nu. The kinematic viscosity is the absolute or dynamic viscosity divided by the density of the fluid. Note the use of the word kinematic to specify a division by density, as with kinematic pressure. There is also a polymesh directory, which specifies the mesh to be used in the simulation. This data is automatically written by blockMesh, so I won't go over it now. Now let's look at the system directory. The blockMeshDict file specifies the settings for blockMesh to use in order to generate the mesh. I'll go through this file briefly now, but for a more complete explanation, please see one of the links in the description. We have the coordinates of the 8 vertices of the block. Then to specify the block, we have hex, short for hexahedral, which is the only option, followed by an ordered list of the indices of the vertices. These indices correspond to the coordinates we specified earlier. Then we have a list containing the number of cells in each direction. In this case, 20 in the x direction, 20 in the y, and 1 in the z. Finally, the relative sizes of each cell within the block is specified. In this case, a simple grading of 1, 1, 1 means that each cell is exactly the same size. We also have a specification of each boundary. The moving wall boundary is type wall, which means that OpenFOAM will check each boundary condition we specified in the 0 directory is compatible with the description of a wall. For example, if we specify a boundary to be a wall, but then specify an inflow boundary condition on the same boundary, OpenFOAM would throw an error. The faces in each boundary are specified with ordered lists of vertices. More information is available at this page, which will be linked in the description. The control.dict file contains a number of high-level controls for how the simulation should run. For example, the simulation will start from start time, which is 0, and it will stop at end time, which is 0.5. If we wanted to run additional functions, for example, to work out the total force on one of the walls, then we would specify it at the bottom in a function subdictionary. It's not present here, so no additional functions are run. Here's an example of a control.dict I used to work out the aerodynamic forces on a supersonic rocket. This function object outputs the forces on the patch wall, and it also calculates the aerodynamic torque on the wall given a center of rotation. More information is available at this page, which will be linked in the description. The finite volume method, upon which CFD is based, relies on a finite number of data points to specify the solution. In reality, each variable, for example pressure and velocity, varies continuously through time and space. So certain methods, or schemes, must be used to convert between the continuously varying quantities and a finite number of data points stored at each cell centroid. These are called discretization schemes and are specified in the fvSchemes file, which is open now. The selection of different schemes is a topic for its own video. For now, this page is linked in the description for further information. For each variable, the finite volume method generates a system of simultaneous equations, one for each cell. These simultaneous equations are written as matrix equations, with a matrix M, a solution vector x, and a right-hand side vector b. Ordinarily, you might invert the matrix M in order to solve this equation, but since there are many cells, the matrix becomes very large, so inverting it is very time-consuming. So instead of directly inverting each matrix, an iterative approach is used to solve the equation mx equals b. These matrix solvers approach the exact solution for x with each iteration of an algorithm. How far away they are from the exact solution is characterized with a residual. A lower residual means the solution is closer to the exact solution. What qualifies as a low enough residual depends on the situation and the user, but generally, 1e-6 is a good number. In the fvSolution file, we see each variable has its own matrix solver, with an absolute tolerance and a relative tolerance. The matrix solver stops iterating if the residual goes below the absolute tolerance, or if the residual is less than rel_tol multiplied by the initial residual. For example, with pressure, if the initial residual was 0.1, then the solver would continue until the residual was below 0.005. Sometimes, depending on the solution algorithm, the matrix solver itself is run multiple times. If so, then different settings can be used on the final run of the matrix solver. In the case of pressure, it copies all the settings from P into P final, then sets rel_tol to 0. This means that, on the final run of the pressure matrix solver, it will keep iterating until the absolute tolerance of 1e-6 is reached. The piso section contains settings for the piso loop. For more information about the piso loop, please watch the video linked in the description. One last thing to note is the pref settings. For an incompressible simulation, the absolute pressure is never used. Only the differences in pressure have any effect on the fluid flow. So if none of the boundaries specify an absolute pressure, then an arbitrary cell can have its pressure set to a fixed value. This way, the absolute pressure elsewhere in the fluid can be found from the difference in pressure relative to this cell. Here, cell 0 is specified as the reference cell, with the reference value of 0. The last file in the system directory is blockMeshDict. This file is equivalent to the other blockMeshDict, but uses a newly added syntax. The foam.foam file is completely empty. Its sole purpose is to have a name with a .foam ending, so that ParaView knows that the directory is in OpenFOAM format. In the log files, we see the log output of blockMesh and icoFoam. Looking at log.icoFoam, we see a standard log file header, some initialization steps, and a log of some solution metrics, for example, the residuals. Each time an equation is solved, a line is written showing the matrix solver used, the variable being calculated, the initial residual before any iterations, and the final residual after the iterations. For example, at time equals 0.005, we see that the x velocity started with a residual of 1 and ended at a residual of 8.9 times 10 to the minus 6 after 19 iterations. There is also a log of the current number. This is a dimensionless number showing how large the time step size is. This value is calculated at each cell in the mesh. For icoFoam and similar solvers based on the piso loop, the current number must never go above 1 anywhere in the mesh. Otherwise, the solution may quickly blow up to infinity. For more information about the current number, I highly recommend this video by Fluid Mechanics 101, which will be linked in the description. Finally, there are the time step continuity errors. Again, these show the amount by which mass is not conserved. The continuity error is calculated at each cell in the mesh. If the error is positive, then mass is being generated in the cell, and vice versa. The continuity error is summarized in 3 ways. Sum local is the sum of the absolute value of the continuity error in each cell. Global is the sum of the signed continuity error in each cell. Cumulative adds up all the global errors of the previous time steps. For example, if we had 3 cells, each with continuity errors of -1, +0.5, and 0, then the sum of the local error would be 1.5, while the global error would be -0.5. The log.blockMesh file similarly starts with a log file header, some initialization steps, and then a log of creation of the polymesh directory. We've now gone through every file in the cavity tutorial case, so this marks the end of this video. Thank you for watching.